Welcome to Opening Voices. I'm Quentin, I'm CEO of CleverCloud. We are still discussing with Philippe Notton, the CEO of SiPearl, the European company specialized in processor design. In this episode, we are talking about SiPearl and its core business, processor design in Europe. Hello, we're still with Philippe Notton from SiPearl, and I'm Quentin from Opening Voices. We are in Paris. We are speaking about microconductor and what we can do in Europe to build a CPU. So in the last two episodes, we have the discussion about the market, what is semiconductor, and all the market is the structure to produce these so-called chips that allow you to see some nice cut GIF all the time. What we can discuss here, Philippe, is about to say, okay, SiPearl is using license of ARM instruction to build and design its own instruction set and design it, and TSMC is producing that. Mm-hmm. So the company have been created in 2019, so it's about like 5 years old now. Today, what is the company size, for example, number of people to design this kind of stuff? What is the number of people you need to do those?
Today, we have 5 R&D sites, 4 in France, 1 in Spain, about to open in Italy. We have 200 persons and it's around 150 engineers. So 75% of the staff is R&D centric.
And to design stuff, so you design the CPU. And how do you design it? It's basically a paper and pencil, or it's
on the whiteboard, so it's so easy to do. Now, we first, in terms of R&D, we have about half of the R&D is software, half of the R&D is hardware design. Why software? Because we need guys to develop a Linux kernel, BIOS, and all the components you have in a motherboard. And after, for the hardware, the design of the chip, you have different expertise from architecture, design itself, implementation, which is the way they are going to draw all the tracks and the gates in the chip, and a team which is the one focused on production that will drive TSMC and to ensure that when the chips are back from the factory, they are working perfectly.
Ordering a chip at TSMC is not like just drag and drop a chip and click add on the car.
No, and especially because when you spend a couple dozen $1 million for the fab, you are not going to send it as is. So it has to be fully tested, emulated, simulated before to ensure that what you send to TSMC is exactly what you want it to do at the
simulation is something simple, I feel, no?
Yes, also it's so easy. No, it's easy to simulate when you have one gate. So one basic element on the chip.
When I was in engineering school, I do it. I have done my own CPU and simulated it.
Yes.
And you have like 48 gates, something like that.
And now we have 60 billion gates.
Okay, so
all of them are useful.
I assume the software I was using in the time is not the same, isn't it?
No, that's why it's kind of exponential complexity. And the more gates you have, the more complexities, the more test cases you have. And these 60 billion gates, all of them have to work in proper order.
And does there is a market of this kind of software? Or is something you need to buy or build yourself or making at home? So what is exactly the number of stuff you need to do inside buying on the market? What is the level of secret?
So if by software, you mean the design software?
Yes.
In French, it's CAO, or in English, it's EDA, electronic design automation. That's all the tools we need to have to design the chip. If you have a writer, you just need to have Microsoft Office, that you will spend it 10 euros a month to have it. In our cases, we have a huge pool of software we have licensed with plenty of different products to help us during the different phase of the design, to design, to test, to emulate. So it's very expensive, and we have guys which are expert in all these tools, because today you don't design a chip, and especially a CPU, without a fully, let's say, a full batch of design software. Plus the data centers we have built, where we push the design, we simulate the design to
ensure it. For example, I know that simulated the design is a complex stuff that you don't do in traditional hardware?
So you can simulate by software. After, if you want to simulate at so-called gate level, it's huge in terms of compute time. We have one of the largest machines in Europe called it's an emulator. It's a rack of FPGAs where we can drop into this rack of FPGAs an image of the chip. And this chip will work at something like, let's say, 500 kilohertz instead of 3 gigahertz. But at 500 kilohertz, you can start the software. So the Linux kernel will boot in a couple hours. Just 3 hours in our cases.
And starting to simulate and see how everything is working here.
So that you will have a shell with you can have an hello world. You will see that the kernel will boot and will not add in kernel panic. It's a good sign. So it means that plenty of gates in the chip has already been used. You can start to have communication over PCI. But now the drawback is that in emulation, it takes time, but it's reasonable. So you can wait a couple hours, or if you send a batch on Friday, on Monday morning, you have the result of the emulation. And with this, you limit the risk because you can fix them during the design phase and not after the production. Because if you fix hardware bugs after the production, it's complex because it's a new spin and lots of expenses to do.
But basically, if you find a bug, you will need to fix the bug, then relaunch the simulation, which means like lowest cost of minimum bug in the design will be 1 or 2 weeks fix just to get the simulation result.
We have some so-called run which can take a couple weeks, but anyway, compared to an issue in production, it's nothing.
And yeah, just to understand the feedback loop, because basically, if you're a developer, you just like write a web page, it refresh on the browser, and you have your feedback loop. But there, the feedback loop of something, it's about 1 or 2 weeks minimum time. It can be bigger for a bug untangling with memory and stuff. That will creating a long time to debug the stuff, which is elongates the time from an industrial point of view. And for sure, it's way less expensive than producing the stuff, putting the chip and say, oh, it doesn't. Oops. How many of this we have produced? 1,000. Oh, that's nice.
So in this case, this is not an option. Everything has to be tested before. Simulation, emulation. So yes, it takes time, but it's much more reasonable and as the, let's say, standard flow now to develop such a processor.
Okay. And so you have this, which is creating the stuff, and you have also other kind of. So when you have this simulator, for example, this simulator is something like you can buy like off the shelf and something, or it's something you need to build up, assemble. Like for example, how Intel or AMD works on this. Does they are buying product on the market, or is this kind of private cooking system they have?
So the competition is not necessarily disclosing its design secrets, but it's not rocket science. We have access to the same design tools, to the same emulator. We just know that in US, companies like AMD, they have 10x or 20x our capacity in terms of computer emulation. So we are, let's say, followers on it and with different budget, but that's the same. In fact, it's kind of STEM and standard methodology.
It's standard methodology, but it's not very well available in the market. So if you need to produce this kind of industrial tools, such as the simulation data center you have, and all the software stack and software pipe to produce that, you need to have like maybe 20 to 30 people at home that are just
focus on this, and we learned a lot. Today, our chip, Area 1, the first one, is the largest and the most complex silicon design in Europe. So we had to build this expertise and learn from scratch how to do it. Learn how to use these tools, to debug the tools, to build the emulator, to build our own data center for your compute farms to the tools. Yes, because it's not that we upstream some bug fixes, but there are, let's say, strong and day-to-day discussion with our support team to fix some bugs which happens after on the next release.
So basically, it's not simple to do this.
No.
It's basically a lot of industrial tools you are producing there, and you need more money to be able to have multiple simulation racks to be able to have many simulation working on the same time on different part of the CPU if you want to fix faster the point.
In our data center, in our data center, we have more than 300 servers to help us just to design the chip. Plus the emulator, which are, let's say, very specific hardware. So all the logistics.
So it's a very specific hardware, the emulator hardware?
The emulator, yes, it looks like racks, standard racks, but it's just blades of FPGAs, where you can have in 2 racks, or it's not 2 racks, it's probably 4 racks, something like this. You can have a rare one of a CPU, which is working in emulation. It's the same one, even with his PCI interface. Even the memory is emulated. It's just much more slower than the chip, let's say, used in real life. It's at 500 kilohertz instead of 3 gigahertz.
And if you have like magical wand, for example, if you have like 3 times this kind of racks, does it will accelerate SiPearl or not?
Yes, because in this case you can have more engineers working on it.
In parallel and goal and velocity. Yes. And that's basically how Intel or AMD does.
Yes, because they have better capacity. Doesn't mean that the emulation would be faster, but you can have more engineers, so you can use multiple test cases or even start, let's say, working on advanced software on it.
Okay, and today you cannot because you don't have the financing to do it.
We spend already a lot in emulation, so doing more today is just, let's say, impossible.
Okay,
but we are quite happy. You are reasonably happy about this because we have an emulation capacity which is unique in Europe.
And does there is other company working on this kind of stuff in Europe or not at all? So that means that maybe you need to recreate the kind of skills that nobody have here.
That's the challenge we have to. So building such a team took time. Now the guys are, let's say, very good, but we spent years in learning how to do it. It's really when you are creating an expertise from scratch. We cannot, let's say, recruit engineers from US or these places because they don't want to come to Europe. It's going to be also different class of salary. So we created from scratch. We are even involved with engineering school to push the school to produce engineers, let's say, focus on this kind of technology. And here we are in, let's say, long cycle. But yes, it takes time. The pity is that the jobs are fascinating. The product is quite exciting. So but step by step we'll be able to do it ideally. So other companies like SiPearl should do it also in Europe. That's the way you create an expertise and pool of an ecosystem.
So and companies like maybe Visora that creating a calculation system for AI, which use the same kind of tooling at this point, but it's less complex to do it.
Yeah, it's an accelerator, not a CPU, so it's not exactly the same design, but in terms of methodology, design flow, design tools, yeah, they have access to the same pool of products.
And the SiPearl is maybe the biggest company on the area, so basically you can help other company by driving the ecosystem.
That's the cost of being the pioneer, and so pushing the schools to produce engineers, creating expertise, ensuring that our engineers will stay with us. So we need to sell them, let's say, very exciting products. But yes, you're right. We need to develop an ecosystem, such as the ecosystem which exists in California, which exists in Texas, in Austin, which exists in Tel Aviv and Jerusalem in Israel. Today in Western Europe, we are not at this level. We are pushing for it. The engineers are good. They just need the project, and to have this kind of project, they need the money or the equity to build startups.
And if we speak about what does SiPearl, so you are currently on the phase of polishing the design before the production of the first CPU, isn't it?
We are at a couple weeks from the production to fix last-minute bugs and ensure that we'll have, let's say, a very, limited number of bugs in production.
Okay.
That we can fix by software, something like this.
Yes, because at the end you can just kill some branch of the CPU and say, okay, no worries.
Or a software fix can do it. So it's a question of, let's say, risk mitigation. So if you go to production too quickly, you have to, let's say, too many bugs at the end.
And it will reduce the capacity of the CPU at the end.
Another way also, yes, if you reduce the clock, so if the chip is slower, you clock it slower, you limit the risk. But The deal is that the more advanced is the simulation, the computation, the emulation, the layout, the better will be the chip in performances also. Just at one stage you say, okay, now we are good to production. We are good for production. We go for it.
Okay. And this CPU, so we will discuss with Craig in next week about the market and where we will use the CPU. Basically, there is other people working on central processor unit for server or laptop in Europe or not?
Not to my knowledge. On acceleration, yes.
On acceleration?
On pure CPU, no.
On acceleration, you have like Visora, you have Spin Cloud.
Spin Cloud is Quantum.
No, they have made the switch to like everyone this year. They have you know what? We discovered that our CPU, our accelerator is so good at making LLM working faster. The joke is if you go on some, for example, like you have open EuroHPC conference, for example, in Krakow like a few weeks ago. Basically, you will have every producer of semiconductor which go there, because even if you're not on the HPC market, this is where you will be able to talk with people about HPC, about semiconductor, about everything. And basically the joke is everyone this year was about to explain how what they do is very good for LLM. Like memory is good for LLM.
That's the next big thing.
So there is a lot of sales to do there, and so there's Visora, Spin Cloud,
Accelera
in Holland.
You had Calray in Grenoble,
which is also, so SiPearl is a partner of Clever Cloud in many research projects. I haven't disclosed this before, but we do a lot of press release about that. So we work together at this, and I'm very proud of working with that. And I have to say that the engineer I have met in SiPearl are one of the best I have seen.
I'm glad to hear this.
And very, very interesting to talk with these guys. And what we are working together is very, very exciting. And maybe what can be interesting there is also, so we also work with Calray on DPU. So everyone is knowing each other on the market, but nobody else is working on the CPU. So basically, SiPearl is not making out. We will lose all this expertise we are going to make there. And if we want to fulfill fab in Europe one day, we need all these guys to be up and
you need all the products to fill up the fab. Yes. That's why TSMC arrived in Arizona, because they have all the US products. Because they will Qualcomm, NVIDIA, the one from the GAFA that could load this fab. Apple, yes.
So that's why that's how they will load this fab. But today in Europe, you cannot load the fab with Calray, SiPearl, and Visora.
Not at all. Yes.
It's about like 15% of the fab capacity or something like that.
No, it's below 1%. That's if you take all the startup accumulated in Europe today, it's even not 1% of the fab. It's no, we're not at this stage. You need some huge pipe like Apple. It's huge volume in consumer. The GAFAM, because they are big die, so it's big wafers and let's say good volume. No, today we are not at all ready to have a fab.
Okay, so less than 1%. So that's why we need to work a lot to raise this market, which is a market that nobody understands really. And it's quite complex to explain to the people. And that's why I want to do this podcast, because I think it's very important for the people to understand what we are doing there. So what the future, so in 5 years, you have built the whole industrial stack to design your product and to creating the good connection with TSMC. Yes. Because creating the connection with TSMC was not like so easy. It's not like giving them a phone call saying we have a CPU to produce. I send you the design in a mail like right now, and can you call me back by Monday with a quote?
I need to wire the money also for this, not only the design file. No, to be honest, if you have the money, TSMC is open. There is no free lunch, so you need to pay them a lot for the services. It makes sense. But the way they have structured TSMC, it's open. So you can do it. Definitely that today, if you want.
Even if you are producing like less than 1% of the fab.
It's not volume related.
Okay.
It's the access to the technology. Today, producing a chip in 5.3 or 2 nanometer, that's very expensive. 15 years ago, producing a chip in 65 nanometer was much more reasonable. Now it's just a question of scale. And there are not so many candidates to do it. If you have the money, if you have the design team, the money, the product, you have access to that.
Okay.
So it's not that complex. It's much more question of resources and.
I see we are a little bit behind the clock. Maybe just in 1 minute. So I'm pretty sure that what you are doing there, it will be a huge success. But if you have 1 or 2 recommendations about what's make you slower and not delivering enough inside what you are building.
Access to human resources. Building a team takes time. You need to recruit the guy. You need to try them, or they have to be self-trained to understand the way to.
Because there is no learning center for this kind of stuff. So people need to read books, go to conference to speak with other professionals, and it takes time to build up the team.
In this segment, yes. If you are in the web business and you are building a SaaS platform, you will find a CTO or VP of R&D that has done this 10 times, even in France. For what we do, it just does not exist.
So you need to create it.
We need to create it. And to create, you learn, you try, you fail, you retry, and at the end, you're good. So this takes, this takes time. After, there's the access to cash, equity. So licensing of course, you need to pay the guys, but licensing the tools, building a data center, this is over expensive. The access to TSFs, it's over expensive. So the budget spent on a first chip is just completely crazy. We are talking about 9 digits. It's completely insane, the amount of money you have to involve on it. So it takes time to find it. And this culture of risk and raising equity in Europe for semiconductor, even if everybody's talking about semiconductor, but this culture of risk just doesn't exist. So it's quite complex to finance these kind of operations. Even if we know at the end we can make lots of money out of it. So I say it's not California, it's not Israel, it's Western Europe. So now we have good investors on board, but it took time to find them.
Okay. So maybe we will discuss the market with Craig next week. I have to say thank you, Philippe.
Thanks for the invitation.
The time to explain a little bit the market and what you're doing there. And I hope we will see the rare one quickly soon.
In your data center.
In my data center, it's already signed. So thanks a lot. See you next week, each other. We will continue this discussion about semiconductor. Thank you for listening Opening Voices. We will continue our interview with the SiPearl team in a few days. So follow us and subscribe not to miss our next episode.